Question 2 for the 2012 Scholarship Physics paper, NZQA, NCA. 75 watt electric light bulb. This is on inductance with zero inductance. So the light bulb, as you know, is a coil of wire wound up really tight, and we're considering it to have zero inductance. In practice that might not be true. You can test that for yourself. Switch on a filament light bulb and have a look. See if it slowly switches on. Anyway, that's a sidetrack. It's designed to run from 50 Hz AC supply, 120 volts RMS. If the only supply available is 240 volts RMS, 50 Hz, and the bulb can be operated at correct power by placing in series with a resistance or an inductance. Find the values of the R and L and the power drawn from the supply in each case. Okay. Firstly, we'll do the resistance. So the resistance of the resistor placed in series with it must equal the resistance of this is resistance. The resistor must equal the resistance of the bulb. Otherwise, you're not going to have an equal voltage drop, which will add up to for the voltage drop across both resistors to add up to the 240 volts. And I'm talking about the bulb as a resistor because that's effectively what it is, because it has zero inductance and it clearly has no capacitance. So what we need to do is find that resistance. I'm not going to do the full calculation, I'm just going to show you how to work it out. You can rearrange your power formula, combine P equals I times V with Ohm's law, V equals I times R, and rearrange it to make it in terms of P, V and R, because you have the power, you have the voltage, you need the resistance, so that'll work out to be V squared over R. And that R we're talking about there is the resistance of the, this is the power, equals V squared over R. I shouldn't have that like that. We need the resistance, that's what I'm getting to. So we know the power and we know the voltage, 120 and 75 watts. We can rearrange for the resistance of the bulb, and that'll give us the resistance of the bulb excuse me, when you plug in the numbers of 192 ohms. You will also need to know the power. The power for when you have both of these, resistor and the bulb in series, is going to be twice the 75 watts of the bulb, because they have equal resistance. The current flow flying through them is obviously the same. So the power usage must be the same, P equals I squared R. So 2 times 75 watts is going to be 150 watts in total. Part 2, we want to know about the inductance, and this gets tricky because we have all of our phase relationships. If we consider the voltages, we know the voltage across the resistor has to be 120 volts RMS. We'll just stick with that for now. The voltage across the inductor leads by 90 degrees, and that's going to be our question mark. We don't know what that is. Our supply, we're told Vs is 240 volts RMS. So we're looking for this length here to get the voltage across the inductor, and then we can use that to find, and we can work out the current in the circuit using power formulas, and we can use that to find the reactance of the inductor, and then we can use it to find the actual value of the inductor. So let's just quickly show you what that would look like. So VL is going to equal the square root of Vs squared minus VR squared, so it's 240 squared minus 120 squared. That'll give you a particular number, which I'm not going to deal with right now, because we're just interested in the method to give you help with your scholarship. You can work through the numbers in your own time. Next thing, we know that the reactance of the inductor, this is like resistance for Ohm's law, R equals V over I. The reactance equals the voltage across the inductor over excuse me, the current running through. The current's always in phase with the resistance, so, and we've just calculated VL from above, so it's going to be VL over the resistance. I equals P over V, okay, from our power formula, but this time it's the power of the bulb, which was 75 watts, so it's going to be 75 watts. I'm just put that as a little, it's not actually part of the equation, and VR, because that'll give us the current running through that resistor. Okay, that's I of the resistor, and then that gives us XL. We can remember XL equals 2 pi FL. We know the frequency is 50 Hertz, we know 2 pi, and we now know this XL from all of our earlier calculations, and so we can rearrange for L. So now we have the inductance. We just need to know the power drawn from the supply, and that's easy. The power is going to be a total of 75 watts, and it's only the power through the resistor that we have to consider. The inductor, whatever it takes from the circuit, it puts back into the circuit. Okay, that's the nature of it. So that solves that. Nice. B. Alternating voltage is applied across a coil wrapped around an iron core. An aluminium ring around the core will float at some height above the coil. And we've got a description, our diagram there. You see the floating aluminium ring. I'll talk about that in terms of being a ring. We've got this coil wound all the way around here, connected to an AC alternating current supply, and an iron core to magnify the magnetic field. And it says the thin iron sheets glued together. So you can see that it's kind of a laminate. And it talks about a laminate later. Anyway, explain why this happens. They want to know why the floating happens. This is going to be more of an explanation than an actual specific written answer once again, because I just don't have time to get into the full details. But basically, you're going to get a change in current, regularly changing current from the AC supply. This will give rise to a change in magnetic flux in the coils. Okay, in the coils. The change in magnetic flux in the coils will be shared by the ring, so there'll be a change in magnetic flux in the ring. This leads to an induced voltage in the ring, according to Faraday's law, which leads to eddy currents flowing around the ring. So I'll just carry this around, eddy currents flowing around the ring. Now, the direction of the eddy current will give rise to, excuse me, a magnetic field in the ring. So we'll just, a magnetic field in the ring, a B field in the ring, which opposes the change that produced it, the change in flux which produced it, and that's according to Lenz's law. I'm not writing very well on this, but you get the idea. It changes, opposes according to Lenz's law. So that produces a repulsive force, which pushes it away from the coils of the AC supply. And then when that force is balanced by gravity, so Fg is also down on it while this repulsive force is upward, Fg balances the repulsive force at the height that we have, that it floats, and that's pretty much explains why it happens. So there's a lot of steps there. You could probably cut through some of that if you really wanted to, but you'd have to use very specific terminology to ensure that you didn't miss any of the steps. C. Explain, possibly without with the aid of a diagram. I won't really use a diagram, but how such a coil could be wound so that this effect would not take place. So really, we have to eliminate that change in magnetic flux in the AC coil. Okay, the alternating current running through the coil. So the best way to do that is, I'm going to show a diagram. You would have some coils running one way, and then you would loop them back on themselves so that you would have current running in the opposite direction. So if you imagine you've got one piece of wire with current running that way, right next to it, and another piece of wire with current running that way, the magnetic field from each will cancel the other out, so there will be no change in flux, not a change in flux in the ring, which means there's no repulsive force produced to make it float. Okay. Last one, D. To reduce the heating of the iron core, thin sheets of iron are glued together. That's what we could see from the picture. The glue that holds the iron sheets must have some specific electrical properties. Suggest at least one electrical property of the glue, and state why this is important. The one main property of the glue is that it must insulate. So it must have insulative properties, non-conducting, and that is to prevent eddy currents, because you could get eddy currents induced in the iron core as well, and that would lead to heat loss or it would heat it up, which would be energy loss, and is an efficiency issue that you find in transformers. I before E except after C, efficiency. One of those tricky ones, eh? Yeah, so that more or less covers it. There are probably other other properties that it must have. The marking schedule mentions that it should be permeable to magnetic fields, but one of the tricks there is that the magnetic field is running parallel to the laminate, so I don't know if that would matter. You can think about that a little bit more yourself. Yeah, I think that covers it more than enough. There you go, question 2 of 2012 Scholarship Physics paper. We'll keep working on the rest as we go.